Okay, topic 1, energy part 2. Before we start this part, what I'd like you to do is just pause the video, go back to the start of the part 1 for energy topic 1. You had a checklist that looked like this. What I want you to do is to look at each of the statements and decide red, amber, green, whether you're able to do these things. Red if you've got no idea, amber if you're feeling that you could do it but you mightn't be always so confident, and green if you're feeling that you have no problem with this particular topic. So you need to fill in this checklist and RAG rate each of the parts for part 1. Okay. So for part 2, it's again the same format. We have our checklist, which we'll look at the end of this part. We have some basic facts that are listed and the things that you have to be able to do at the end of this part of the topic. And we're going to turn and look at lesson 1. So lesson 1 is about power and energy transfers. We're given a starter task, which is looking at some of the things that we learnt in part 1 of the energy topic. We're told that a wrecking ball has a mass of 5,000 kilograms. The ball is pulsed sidewards, it rises by 6 meters. When it's released, it swings and hits the building. So I'm just going to put in a little sketch just to make it clear for myself what it is we're saying. So the ball is going to, it's raised up, it's going to swing down to hit the building. So here's my building. And the distance that it's raised up by a distance of 6 meters. Okay. We have to then calculate the amount of gravitational potential energy the ball has at its highest point. Show all 4 steps. So step 1, I write out the numbers. I've got a mass of 5,000 kilograms. Its pulse sidewards rises up by 6 meters, so the height is equal to 6 meters. It's released, it swings, it hits the building. What is the gravitational potential energy? We can assume that the value for the gravitational field strength is 9.8 joules per kilogram. Okay, so next step is we write our equation. Gravitational potential energy is equal to mass times gravitational field strength times height. Third step, we put the numbers into the equation. So the mass is 5,000, gravitational field strength 9.8, and the height is 6. And we put those numbers into our equation to calculate the answer. So we have 5,000 multiplied by 9.8 multiplied by 6 to give us an answer of the gravitational field strength is 294,000 units joules. Okay, part B. Calculate the speed of the ball when it hits the building. Again, show all 4 steps. So what are we told here? Well, the mass is still the same. Height, well, the height is now 0 because it's come down to the bottom. But we know what the gravitational potential energy was at the top, and that's going to be equal to the kinetic energy. Now, this assumes that no energy is wasted because of air resistance. We're going to say that the kinetic energy is equal to what the gravitational potential energy originally was. So we've got the kinetic energy is equal to 294,000 joules. Step 2, well, in this case we're looking at the equation for kinetic energy, which is that kinetic energy is equal to half mv squared. And I'm going to rearrange that, which tells me that, well, v squared, I need to get rid of the half by multiplying both sides by 2. And I need to get rid of the m, so I'll do that by dividing both sides by the mass. And then I have to remember I have to take the square root to get the value for the speed. So that gives me my equation. Okay, number 3. Put the numbers into the equation. So the speed is equal to the square root of 2 times 294,000 divided by 5,000, and that gives me the speed is equal to square root of 117.6. Write out the answer. That gives me an answer of 10.8 meters per second. Now, I would be justified in writing that. I could have written the answer as 11 meters per second. I'm only told one significant figure in the question. I've got two significant figures for my gravitational field strength. So one or two significant figures would be fine, but certainly no more than 1 or 2 decimal points in your answer. What assumptions have you made in the calculation? Well, I already said this. It's assumed there's no air resistance, as no energy is wasted, or another way of saying that is all the gravitational potential energy is transferred to kinetic energy. Okay, so the assumption we've made, no air resistance, so all of the gravitational potential energy is transferred to kinetic energy. Okay, so next part of the lesson, it's about work and power. We've got 2 cranes, they lift identical objects. Both objects obviously have the same mass, 100 kilograms, and the cranes lift the objects to exactly the same height of 10 meters. But crane A takes 10 seconds, whereas crane B takes 20 seconds. And it says to use G is 9.8 newtons per kilogram. And it tells us how much work does each crane do. So we're going to use our usual 4 steps, but I'm going to divide it into 2 parts. I've got 2 objects, A and B, crane A and crane B. And we're going to work out how much work does each one do. So again, start with what we know, step 1. So we know that the mass is 100 kilograms. We know the height is 10 meters. We know the time taken for crane A is 10 seconds. And again, so the mass is the same for B, the height is the same, the time is 20 seconds in that case. And we know the value for gravitational field strength we're going to use is 9.8. Okay, we're looking for the work done, so we need the equation for work done. So step 2. When we turn back, all the way back to, again, first lesson in part 1, this is where we met this idea of work done. Work done is equal to the force times the distance. So we've got work done is equal to force times distance. So we need to know what the force is. We aren't told what the force is here. So we need to think about what force would a crane need to apply to be able to just lift something up. So that force would be equal to the weight. So the weight is equal to mass times gravitational field strength, and that equals to our force. So I'm going to substitute into that equation first of all. So my force is equal to 100 kilograms multiplied by 9.8 newtons per kilogram, which gives me the force is going to be equal to 980 newtons. And then I can substitute that into the work done equation, where work done is equal to 980 newtons. And how far does it move? Well, it moves by the distance of the height times 10 to give me an answer of the work done is 9,800 joules. And in the case for crane B, well, the mass is the same, so the weight is the same, so the force applied is the same, 180 newtons. And the work done is again the force multiplied by the distance, and the distance is the same. So that gives us also an answer of 9,800 joules. So in both cases, the work done is the same. Now, how much GPE or gravitational potential energy does each mass get? By the way, notice it is okay here to use GPE to represent gravitational potential energy because it's in a sentence. It is not correct to use that in equation, so we use EP in an equation. Okay, how much gravitational potential energy does each mass gain? Well, work done is equal to the energy transferred. Okay. So, assuming no wasted energy, that is, we're telling ourselves that our cranes are 100% efficient. So then the gravitational potential energy is going to be equal to the work done. Therefore, the gravitational potential energy gained by each mass is equal to the work done. Okay, right, now last bit, which crane is a more powerful engine and why? So the only difference between these two cranes is that the crane A took 10 seconds, crane B took 20 seconds. So it takes crane B twice as long to lift the mass as crane A. So we could say that crane A has a more powerful engine because it takes less time to lift the mass. Now, another way of saying this is it takes less time to do the same work or to transfer the same amount of energy. So the key thing here is when we talk about powerful engine, we mean one that takes less time to do the same amount of work. And this is something that in a more familiar situation we might say that a sports car, it can accelerate from 0 to 60 in 4 seconds. It has a more powerful engine than a small family car that might take 12 seconds. So it's about how much energy is transferred in a certain amount of time. Okay, so our discussion has shown us that power is to do with the amount of energy that's transferred or work that's done, but it's also to do with the amount of time that that takes. So we can define power as it's the rate at which energy is transferred, or we could say the rate at which work is done. Both of those statements are identical. So we can say an energy transfer of 1 joule per second equals to a power of 1 watt. So we say if we've got 1 watt of power, that means we're transferring 1 joule of energy every second. So we can express that as an equation. This is an equation that you need to know. And we can write that as that the power is equal to the energy divided by time. Or again, we can write that as power is equal to work done divided by time. So P means power, E is energy transferred, T is time, W is work done. Power is measured in watts, energy transferred is in joules, so is work done, and time is measured in seconds. So to complete the sentences, the symbol for power is P, and it is measured in watts. symbol for energy transferred is E, and it's measured in joules. Symbol for work done is W, also measured in joules. Symbol for time is T, and it's measured in seconds. Then we have to be able to rearrange the equation for power to get the equation done for work done or energy transferred. Okay, so work done equals energy transferred. So what does that equal to? Well, we have power is equal to energy divided by time. So I've got energy divided by time. I need to get rid of the divide by time part, and I do that by multiplying both sides by t. So that gives me P times T is equal to energy transferred. So work done equals energy transferred equals power multiplied by time, or W equals E equals P times T. We can also rearrange the equation to get the equation for time. So if I've got power is equal to energy divided by time, and I already said that that allowed me to say that power times time equals energy. I want to get time by itself, so I need to get rid of this P on each side. So I do that, divide by P, both sides by P. So that gives me time is equal to energy divided by power. Time is equal to energy divided by power, or time is equal to work done divided by power. So an energy transfer of 1 joule per second equals a power of 1 watt. Okay, so let's try some of these questions. In all of the questions, we're going to do all 4 steps as usual. Question 1, calculate the power of a light bulb that uses 40 joules of electricity in 4 seconds. So we have the energy is equal to 40 joules. The time is equal to 4 seconds. So that's step 1. Step 2, we have power is equal to energy divided by time. Step 3, power is equal to 40 joules divided by 4 seconds. So that gives us the power is equal to 40 divided by 4, which gives us 10 watts. Then we have the next one. We have the power of a toaster using 200 joules of electricity in 20 seconds. So again, step 1, we write out what we're told. The power is equal to energy divided by time. The power is equal to 200 joules divided by 20 seconds to give me again the power is 10 watts. So the power of this light bulb and the power of the toaster are the same. Now we have the next one. Calculate the power of a clock using 15 kilojoules of electricity in 2 minutes. So again, we'll start by writing out the numbers. And as I write this out, I notice I've got kilojoules, not joules. So I need to convert that to go from kilojoules to joules and multiply by 1,000. Kilo means there are 1,000 of them. And I've got the time is equal to 2 minutes. So again, I need to convert this into seconds. So that's going to be 2 times 60, which is 120 seconds. Step 2, power equals energy divided by time. Step 3, put the numbers in, 15,000 divided by 120 to give me an answer of, don't forget in physics we always use calculator, 125 watts. There are never any questions we are not allowed to use a calculator. Next question, calculate the power of a television. It uses 0.5 kilojoules of energy. So that is the same as multiplying that by 1,000 gives us 500 joules. The time is 5 seconds. Power equals energy divided by time. Putting the numbers in, we have 500 joules divided by 5 seconds. So that gives us the power is 100 watts. And then finally we have calculate the chemical energy transferred by the car. Here we're told that the power is 25,000 watts. The time is 50 seconds. Our equation is power is equal to energy divided by time. which means that energy is equal to power times time. So now we can substitute into our numbers 25,000 watts multiplied by 50 to give us the chemical energy transferred by the car was 25,000 multiplied by 50, which is 1,250,000 joules. Often a good idea in these cases to either write this in standard form, just so that you don't make a mistake with a number of zeros, or you can choose to write this as with a prefix on the units. So 1.25 million joules is the same as 1.25 megajoules. Mega means a million. Calculating the next question, again we're told that the power is 80,000 watts. Again, the time we're told is 60 seconds, so we're going to use power is equal to energy divided by time. But in this case, actually, my mistake, that's not the equation we want. We want the equation power is equal to work done divided by time, which gives us work done is equal to power times time. So work done is equal to 80,000 divided by 60. So that gives us the work done is equal to my mistake. Work done is 80,000 times 60. So there's my mistake. Fortunately, I'd written out my equation, so I see I substituted in incorrectly. There's a multiply here, not a divide. So my answer is 80,000 times 60 to give me an answer of 4,800,000 joules. And again, I'm going to write that using the prefix, so it's 4.8 megajoules. Then the last question, how long does it take a microwave of this power to transfer that amount of energy? So going to have the power is equal to 0.2 kilowatts. So that gives me the power is equal to, again, need to multiply by 1,000, so that's going to be 200 watts. And we're told that the amount of energy transferred was 10 kilojoules. So that gives me the energy is equal to 10 times 1,000, 10,000 joules. The equation is power is equal to energy divided by time, which gives us that time is equal to energy divided by power. And I can substitute the numbers in. That gives me T is equal to 10,000 divided by 200 to give me an answer of 50 seconds. Okay, forward, and here we're told that the power, we're looking for the power, the force is 6,000 newtons, the distance covered is 2 meters, and the time taken is 4 seconds. So we can use here, we need to work out the work done first of all. So work done is equal to force times distance. So that gives me work done is 6,000 newtons multiplied by 2 meters. So the work done is 12,000 joules. So that's now another piece of information that I have. I'm looking for the power, so I'm going to use the equation power is equal to work done divided by time, which gives me power is equal to 12,000 joules divided by 4 seconds, which gives me an answer of the power is equal to 3,000 watts. So this question would be worth more marks in an exam because you have to use 2 equations. It would be worth perhaps 4 marks. And finally, we've got the power of the crane if it lifts a block weighing. So we've told that the weight is 20,000 newtons. It takes it 10 seconds to move it, and the distance travelled is 8 meters. Remember, this W here is the W for weight, so I'm just going to change, that means the force applied. So work done, in this case the W means work done, is force times distance. So work done is equal to 20,000 multiplied by the distance, which is 8, to give me the work done is equal to 160,000 joules. So again, I've got a little bit of extra information. Power is equal to work done divided by time. So power is equal to 160,000 divided by the time, which is 10 seconds. So power is equal to 16,000 watts. It's equal to 16,000 watts. Okay, so more practice questions in a slightly different form here. So in the previous questions, the information is given to us in the question itself, in the words in the question. Here, we're told some of the information in the words and we're told some of the information in a table. So you need to be just careful in this format. When you see a table like this, you may need to get some of the information from the table. So it says, calculate the work done by Carl in climbing the hill. So what do we know? We know that the hill has a height of 500 meters. We're told that Carl's weight, and remember that's the force in this case that's used, is 650 newtons. And we know that the time taken is 5,000 seconds. So what's the work done by Carl? Well, we use the equation work done is equal to force times distance. And we put in the numbers. So it's 650 newtons multiplied by 500 meters. Type that into our calculator, we get 650 times 500 gives us an answer of the work done is 325,000 joules. Okay, now then we're told Victoria is a fell runner. She overtakes Carl and James, and we need to work out what is the power in Victoria's muscles. Okay. So what are we told? We're told we know that the force for Victoria is 500 newtons, the height is 500 meters, and we're told the time is 2000 seconds. So again, we first of all need to work out the work done. Work done equals force times distance. So that gives me work done is equal to 500 newtons times 500 meters, which gives me a work done of 250,000 joules. So that's another piece of information that I have now. Next, I need to work out the power, which is work done divided by time. So power is equal to 250,000 divided by 2000 seconds to give me power in our muscles is 125 watts. Then it says, what is the difference in muscular power between Victoria and Carl? Okay, so what information do we have? Well, we know that for Victoria, I'm going to write that with a V beside the power. The power for Victoria's muscles is 125 watts. We're looking for the power of Carl's muscles. We know that the work done for Carl was 325,000 joules, and we know the time taken by Carl was 500 seconds. So I can, first of all, I can work out what's the power for Carl's muscles. So that's power is equal to work done divided by time. So that's power for Carl's muscles is 325,000 divided by 5,000, which gives us an answer of 65 watts. Now, what it asked us for is what is the difference? So the difference in power between Victoria and Carl is 125 minus 65. So that gives us the difference in power is 60 watts. Okay, right, final set of questions. We have Nina is a sportswoman, her mass is 55 kilograms. We're told in this case to take the value for gravitational field strength as being 10 newtons per kilogram. That's sometimes referred to acceleration due to gravity. That would be 10 meters per second squared. So what is Nina's weight? Well, What are we told? We know that her mass is 55 kilograms. We know that the gravitational field strength is 10 newtons per kilogram. The equation is weight is equal to mass times gravitational field strength. So her weight is equal to 55 multiplied by 10, which gives her a weight of 550 newtons. Now she's competing in a pole vault event. She jumps 3.5 meters. Calculate her gravitational potential energy at the highest point. Okay, so again, we know what her mass is. We have a value for gravitational field strength, and we're told that the height is 3.5 meters. Now, the equation for gravitational field strength equals mass times gravitational field strength times, the equation for gravitational potential energy is gravitational potential energy is equal to mass times gravitational field strength times height. So that gives us the gravitational field strength is 55 multiplied by 10 multiplied by 3.5. This is how easy it makes it. I'm just replacing the letters with the numbers that I've already written above. And so that gives me a value for the gravitational potential energy is 1925 joules at the highest point. Now, what is the kinetic energy just before she lands? So we're going to say, assuming no air resistance, kinetic energy is equal to the potential energy. Therefore, the kinetic energy is equal to 1925 joules. Okay, so for this question, let's take a look at what we know. We know that the speed she throws it upwards is 12 meters per second. We know that the acceleration due to gravity, so our acceleration is 10 meters per second squared. But remember, this is going to be slowing the ball down. So the deceleration. Okay, we're looking for the distance. And is there anything else we know? Well, we know that when it reaches its highest point, the ball will have stopped, so its speed would have gone to 0. So we know the final speed. Now there's one equation. It will be given to you on an equation sheet if you have to use it. This is the only equation that has got u, initial velocity, a, the acceleration, s for the distance, and v, the final velocity, which is v squared minus u squared equals 2as. Okay, so if we put in those numbers, we've got 0 squared minus 12 squared is equal to 2 multiplied by minus 10 multiplied by whatever the value is for s. So what does that give me? That gives me, well, 12 squared is 144, so we've got minus 144 is equal to 2 times minus 10, so that's going to be minus 20 times the distance. So that would give me an answer of, and I can get rid of this minus 20 by dividing both sides by minus 20, which gives me an answer of the distance is 7.2 meters. Then finally it says, in training she can do this amount of work in 5 seconds. So the work done is 900 joules. Time taken is 5 seconds. How much power does she produce? Well, power is work done divided by time. So that gives us that power is equal to 900 joules divided by 5 seconds, which gives us an answer of, remember, always use your calculator, particularly in an exam. It gives us an answer of 180 watts. So in this lesson, we've had a lot of practice of calculations, and the key message of this question is power is the rate at which energy is transferred, or the rate at which work is done, and we can work it out by doing energy divided by time, or work done divided by time. Power is measured in watts, so transferring 1 joule of energy every second is the same as a power of 1 watt.